Here's a two-dimensional projectile motion problem that involves a car driving off of a ramp at 20 degrees, and it leaves the ramp at 20 meters per second, and by the time it gets to the tip of the ramp here, it has attained a height of 30 meters on the ramp, so that's sort of how high it is when it leaves. And so the problem is asking sort of the usual things, and particularly like to know how far the car is going to travel from the ramp. Sometimes that's called the range. We'll call it capital R right there, and that sort of thing. So we just get started right away in the problem, realizing that you can work on this 20 meters per second bit, understanding that there's always going to be two components of velocity at this launch condition right here. Here's your v naught y right here, and this one right here is going to be your v naught x. So a little cramped in there, but there's a right triangle you can form in there. And of course, this 20 degrees that you take from the slope of the incline that the car is climbing up is the same as this angle in here, so that's another 20-degree angle right in there. So you have all your information on the right triangle. And the reason why I'm doing that is because for this particular problem, it's going to help to have the components of the velocity. So if I look very carefully at it here, I can see that v naught x then is going to be 20 times the cosine of 20, and v naught y is going to be 20 times the sine of 20. So I've got the two components in there, and you can even come to numbers on those. In particular, v naught x here is about 19 meters per second, and v naught y is going to be 6.84 meters per second, something like that. So you can get the two components of the velocity there straight up. Now, why do I need that for the how far? Well, the first thing you're going to figure out then is when the car leaves the ramp, how long is it in the air? That goes back to this idea of the hang time, which is something we keep saying is important with these projectile motion problems. How long is the object in the air? Okay, well, you can calculate that straight up using equation 1, and it'll look like this. Eventually the car is going to hit the ground level 0, given that it started 30 meters high. Okay? And it was launched upwards with this initial velocity v naught y here, so it's going to have this upward speed of 6.84 meters per second times delta t minus 1/2 g delta t squared. So this is equation 1 adapted for the vertical motion of this car. So this is y is equal to y0 plus v0 y delta t plus 1/2 a delta t squared. It's just equation 1, kinematic motion, but we're saying, hey, it's going to hit the ground at y is equal to 0. It starts 30 meters high vertically. That was given in the problem. This is the y component of the velocity, 6.84. Delta t is the hang time, and there's the acceleration term with a minus g in there because it's in free fall. So you can look at this equation right here, and it is a quadratic in delta t, but you can't get the hang time to come out. And in this particular case here, I get a hang time of about 3.3 seconds. So the car is going to be in the air for about 3.3 seconds before it impacts. So your range will come right out of that, because now that you know that it's in the air for 3.3 seconds, you can see how far will this horizontal component of the velocity, or the v naught x, how far will that carry it horizontally? That's what the range is. So the range will come from something like this. You can say the range is going to be a capital R. That's where it's going to stop. You can call the edge of the ramp where it started, say this position right here, you can call that 0 right there, horizontally, position 0. So there you go. X is the range, 0. V naught x, as we mentioned before, is about 19 meters per second. Now, you're not just going to put in the delta t because you are interested in the hang time now, the 3.3 seconds, to see how far this 19 can possibly carry it before it hits the ground. And normally there's a half at squared term over here, but that's just going to be 0 because there's no x acceleration. So this is 0 here because ax equals 0. So you can see you have your range equation right in front of you here, and the car will land something like 61 meters from the edge of the incline. That'll be the range in that one right there. Okay. The next problem is a bit more of a test of your knowledge of vectors and putting some things together. But I'd like to know in part B of this problem, what is the impact speed? Impact speed. In other words, when the car is flying through the air like this, it's going to impact the ground right over here somewhere. Now, we determined R in the previous step about how far that's going to go, 61 meters away. But just as it hits the ground right here, say the car is right here, it's going to have this big V vector sticking out of it like that. That's its impact speed. So just before it hits the ground, how fast it's traveling. So we're after this vector right here. And we'll take it a bit further. We'll find the magnitude and the direction just to report the full vector velocity, which is a good exercise in two-dimensional vectors. So let's see if we can get it to work out. Something very important to know. Okay. So what we'll do then is we have to see how the velocity components evolve. Now, we know that the car is in the air for 3.3 seconds. And so we want to see how the velocity components evolve in that 3.3 seconds. So you can do it this way. You know that v is equal to v naught plus a delta t. This equation tells you how velocity components evolve as a function of time. Now in the case of Vx here is just going to be V naught x, and normally you'd like to put an A delta t term here, but again, like we discussed, Ax is equal to 0. And so there isn't going to be any change to the x component of the velocity. So in other words, through the entire flight of the car, the x component of the speed is going to stay at that 6.84 meters per second. So as the ball flies through the air, I think I made a mistake here. This is actually the y component, so the x component of the velocity is going to stay at that 19 meters per second. Sorry about that. It's going to stay at 19 meters per second. So what that means is that this horizontal arrow at 19 meters per second is going to stay on the ball, stay on the car throughout its entire flight through this parabolic trajectory until it hits the ground. So all the way over here, when it hits the ground, it will have an x component of velocity, which is 19 meters per second. That's going to stick on throughout the entire flight. So the only one that's actually going to change is the y component. You can probably sort of see that by looking at the figure. Initially, the y component points up like that and gets smaller and smaller and smaller, and at the very top, the y component is 0. Then it starts growing in the downwards direction until it hits. So we can just find that downwards component of v over here. We'd have everything we need to find the downward speed. And we can find that downwards component of velocity by just using the same equation, only in the y direction. So vy is going to be v0y. That's the 6.84. Minus g, and there is a delta t here, but we know the car is in the air for 3.3 seconds. So that's going to tell us what the vy has evolved to after that much time. And for this particular number, I got something like minus 25.2 meters per second. So lots of nice stuff to talk about here. In particular, once again, the Vx stays constant at 19 meters per second throughout the entire flight of the car. The y component here goes through a drastic change. It goes from 6.84 meters per second pointing straight up right there at the launch to not only changing, but even changing to a negative sign, changes to minus 25.2, indicating that it's pointing down by the time it gets over to the impact spot. And that makes sense. The car is definitely traveling down. So over here, you could say the x component sticks, the y component is down like that at 25.2 meters per second. Now you can figure out what the speed of the car is going to be at the impact right there. So the magnitude of the velocity is always found by the square root of its components. So it's going to be the 19 squared plus the minus 25.2 squared, something like that. That's always how the total magnitude or the power, say, of a vector, the strength of a vector can be found. And for this, I get something like 31.4 meters per second. So this will be the impact speed of the car just before it hits the ground. So you can see a lot of changes as the car goes through its motion over here. It was launched at 20 meters per second, and because of gravity speeding up as it fell through that second half there, it actually hits the ground at 31.4 meters per second. It's definitely going to hit the ground faster than it was launched off the ramp. The last part about this, and here's your test of vectors, is can you find the angle? Like, can you report the full angle that it's going to hit the ground as well? And I say you can, because when you think about the components you have, when you think about the 19 and the 25.2, you can sort of draw them and say, here's a Vx right here of 19, and if I wanted to draw a Vy of 25.2, well, that would look like this, 25.2. And I'm interpreting the minus sign there as down, so I'm drawing the vector pointing in that direction. And so if I wanted the full vector now, that would just be this hypotenuse, which connects the two legs, which are the components of the vector, the 19 and the 25.2. So there's the vector right there. And we found the magnitude of it to be 31.4. You can tell that's why we use the Pythagorean theorem. It just comes from a figure like that. Now, if we want that angle, I'd have to put in some sort of angle right here, like angle alpha like that, something like that. And I can find alpha now just by using some trig. In particular, it looks like from the figure here that the tangent of alpha is opposite over adjacent. So that's going to be something like the 25.2 divided by 19. And from that, I can compute alpha using the arctangent on my calculator to get 53 degrees. So if you wanted to report the direction the vector is going to have at impact, you would say that it impacts the ground at 31.4 meters per second at an angle of 53 degrees, and you can say something like below the positive x-axis. That's one way to say it. Or you can say 53 degrees south of east, something like that. Some unambiguous label to say exactly what the direction of that vector is going to be. And that's the impact speed, 31.4, but when you add the direction, that's the impact velocity that the car is going to have when it slams into the ground. Over here. Fun stuff, huh?